This video shows you how to reduce the RAM usage for HFSS simulation and also how to reduce the simulation time in HFSS simulation. So this video I tried to create because of many feedback on the users on the simulation time taken by the uh, HFSS solvers. I can see one important thing in the academic area where people are not aware about how the computation working in the background. Let me first go into HFSS, how the solver is working. Okay, so you can see this, there is an antenna, so 2 by 2 antenna over here. And when you are going to simulate this antenna on an HFSS, you will see that it automatically uh, start meshing. So not that any numerical simulation tool, they are actually solving your Maxwell equation on the mesh, not on your CAD. So creating a right mesh in order to get an accurate result is very, very important. So in order to get that accuracy, what HFSS do is it was adapted a technology called adaptive meshing. So initially the mesh will be looks very coarse, and as your time goes, you will see that mesh became more and more stronger. So you can see there are multiple plot of S parameter here. You can see, and these are the S parameter corresponds to each mesh scenario. So initially start with a very coarse mesh, then it will adapt the mesh to next stage. That's called adaptive pass 1. And they will check what is how the S parameter look like. Then what it will do is it will adapt it again. That will be S parameter 2. Then see how the S parameter between my current mesh and previous mesh. Is it deviating a lot? Then HFS will mesh it again. And it will mesh it again and again till your S parameter became finer and finer. So you can see now the S parameter is looks like uh, going to be better, and you can also see the mesh on the structure is not uniform. It has adapted the mesh wherever it's required. So that always ensure that the result will be more accurate and you are not over meshing the structure. So it will automatically find out where to be meshed, and that mesh will be using for the simulation. So you can see as my mesh size goes up, there is not much variation in my S parameter from my previous mesh and current mesh. So that settings actually determines the accuracy of your simulation or reduces memory simulation and simulation time is first steps you need to do is upgrade your HFSS into latest version. Most of the academic students and research people, they are still working on 2015 version of HFSS on their latest laptop. There you will see a lot of difference between the simulation time and memory. And every version of all the solver, whether it's HFSS or any other simulation software, every version they will try to improve the user enhancement. They will try to improve the solver performance in terms of reducing the memory utilization, speeding up the solver performance, and simulation time parallelizations and so on. So this is very important to do these steps by upgrading your current HFSS into latest version. Second one is I'll show you demo on how to set this number of core. By default, HFSS may be setting only single core for your simulation. So it depends on your the available core in your simulation. You can set the number of core. You can also set the RAM limit. By default, it is 90. So you can increase the RAM limit up to 99%. Then there are different solver in HFSS. So coming into these settings, here in the general setting, you will mention what is the frequency you want to mesh it and other thing. And in the option tab, there are option to select different solver. So the direct metric solver is nothing but it directly solving the FEM domain. The iterative solver is nothing but it tried to calculate the inverse of metrics by doing iterations. So what is mean by inverse of matrix? The matrix inversion is the one which is taking a lot of memory for the direct matrix. So one option is I know I have a matrix A and I want to calculate A inverse. So what I can do is I can just approximate A inverse as some other metrics, and I know that if I multiply with A into A inverse, it will be identity matrix. So what I will do is instead of A inverse, I will assume a matrix called X, and I will check whether when I multiply these two together, can I get I? If I'm not able to get I will keep updating x into x1, x2, x3, x4 up to couple of iterations and try to make these x into a inverse. So iterative solvers, the advantage is it can drastically reduce the memory consumption. We will check into that one. Another one is domain decomposition solver. Coming into domain decomposition, it is mainly for distributed simulations. It can distribute it like in the same machines. Let's say I have a very good hardware of 8 core or 12 core. I can distribute my mesh into different core in a single machine. Or let's say I have a distributed machine where the cluster simulations are going on, or I have a multiple machine in my lab where I can distribute my simulation. It's, the my decomposition actually distribute their mesh into different machine and solve it, then combine the result together. So domain decomposition, I will prefer to use if your simulation model is very big, unless otherwise this two solver is quite good. So we are going to compare some simulation, and before doing that, let me do a demo on how to set number of cores and other thing. Okay, so I have one simulation over here. You can see a antenna which is working at 5.9 gigahertz. So you can see an antenna, and this is working at a 5.9 gigahertz. And I want to set number of core and RAM limit for this. First of all, what I will do is I will double click on the setup, and here I will set my frequency and the adaptive passes. So this many number of adaptive meshing will happen during the simulation till it reaches the level of delta S. So current mesh S parameter and previous mesh S parameter, if it is less than 0.02, till that level it will keep updating its mesh. Once it reaches this mesh, this value of S parameter less than 0.02, it will stop it. For antenna problem, 0.02 is sufficient, because most of the antenna problem we will be looking into an S parameter of minus 15 to 20 dB. If you want to see more than 20 dB, 30 dB accuracy, then you can reduce to 0.0 to zero point 0.1. So most of our antenna simulation, you can say 0.02 is sufficient. Another thing is how to set number of cores. So you can go here and click on the HPC and click on the edit button. In the edit button, you can see there is an option to set number of core and RAM limit. So number of core will reduce the simulation time by parallelizing the simulations, and number of the percentage of RAM, which will allow you to set proper RAM utilization by the solver. Okay. So first of all, what you need to do is open your task manager, and on the task manager, you need to check how many core you have in your machine. So what I will do is I will just go here, I will open my task manager and see over here my performance of my machine. If I click on CPU, and it will tell you there is 6 core in my machine and 12 logical processor. 12 logical processor is coming because of hyper-threading. HFSS solvers are mainly working on physical solver, so I can go up to 6 cores. And you can also see I have a 32 GB on this particular machine. So it's okay, I can. And most of the time you also need to know that without running, I'm not running any simulation in my machine, but still 14.6 GB is already occupied by other softwares. And that you need to be careful here. The problem is that uh, even though we say I have 8 GB or 16 GB machine, already good amount of RAM may be using by the OS and other applications. So if you are running out of memory, make sure you are closing all the unnecessary softwares which are there. Close everything so that you can free up the lot of memory. And these values I can see in CPU. The 6 core is free in my CPU. I can use 6 core for hybridization, the parallelization, and set the RAM limit. And as I mentioned, HFSS simulation convergent on S parameter, right? And sometimes people would like to see the convergence on gain, convergence on radiation efficiency. Yes, there is a possibility of HFSS to do the convergence. And what you need to do is there is an expression cache setup. And over here you can say, I want to converge on my radiation efficiency. So usually as parameter is a one HFS by default converge, but there is an option for you to converge it on different parameter. So I'll go to option antenna parameter or far field. Better to go with the antenna parameter. Then you will see all kind of antenna parameters over here. So I can say radiation efficiency I want to converge, add into calculation and click over here. Then the convergence comes as none. What you need to do is click on this and set the number of percentage of convergence. 1% convergence is sufficient for radiation efficiency. Click OK and then run it. Now, if you run the simulation, what will happen is instead of as parameter convergence, it will also make sure your antenna going to converge on expression cache too. Okay, so this is a one steps, and let's go back to our presentation. So here, what I did is so far we discussed about different three solvers. So the solver settings I will discuss, and in the HO simulation. Before that, let's discuss about another important thing. It's called basis functions. So basis function you can see under the same window over here: zeroth order, first order, second order, and mixed order. And as you mentioned, as you know, the HFSS or FEM solvers, it's also an electric field, and it try to calculate the unknown electric field from each tetrahedra. Okay, and zeroth order, first order, second order, these are this polynomial in order polynomial that describes how electric field is varying along the tetrahedra edge, phase, or volume. So if I choose zeroth order, what will happen is from a single tetrahedra, it actually calculates its unknowns of electric field. If I use first order, it actually calculates 20 unknowns of electric field. Second order, 45 unknowns of electric field. So that means if I use zeroth order, then I need to have a more number of mesh to get a good convergence. If I have a first order, I need lesser compared to zero. If I have second order, I need even lesser mesh is sufficient, but computation time for each basis function will be different. Mixed order, what it do is it intelligently assign different basis functions to different part of the geometry. So you don't have control, but solver will automatically assign it. So these are the main steps where you can try how to reduce memory on the solver side. Okay, one on this different solver, another on the basis functions. So let's see how this is going to impact. First, what I did is I took a filter model. I'll show you the filter model. This is from the example model of HFSS. And you can see if I use direct matrix and I choose a first order as a common for different solver. So you can see I used direct solver. The simulation time is just under 4 minutes and memory usage is 1.17 GB. And this is around 1.5 GB center frequency filter. And iterative solver, it took 4 minutes 25 seconds lesser time. And note that if you are using lower version of HFSS, I don't prefer this thing because this is improved a lot in latest version of HFSS. Okay, and you can see domain decomposition, it took 6 minutes. It's mainly because if you divide the mesh into different core, like 6 cores, it actually, it's not very easy to divide into 6 core, right? You need to add a lot of additional header and footer and combine everything after computation. So if you try to decompose your model for a very simple model, it's going to take a lot of time. And most of all the simulation taking almost same memory. That's good point. And you can see the iterative performance good. A couple of seconds variation between direct matrix and iterative. So simple model I will prefer. You can go either with the iterative or direct basis function point of view. You can see the first order which simulated just under 4 minutes and this is 6 minutes 1.19 GB, but mixed order in the memory point of view, it took 1.13 GB. So mixed order taking lesser memory compared to all other basis function. So you can choose iterative with the mixed order or direct with the mixed order. That will be the best memory, lesser memory consumption solver. But you can see it has some more simulation time taken. And also you can see the first order took 9 passes to get a converged mesh, and second order took only just 6 adaptive passes because it each mesh will calculate 45 unknowns here. That's the reason. But you can see it took more memory because if you want to calculate more unknown, you need to have more matrix dimension going to be. That's the reason. And over here you can see mixed order. Mixed order it's took 10 adaptive passes, and this one run on my laptop with 32 GB, and this is the result for first order, second order, mixed order, all are giving same result. So don't worry about choosing different solver, all will give you same result, but you can reduce, you have option to reduce it. Let's see another one. This is a the filter model which is working at 38.5 gigahertz. Okay, and you can see this is the how the field is propagating, and here you can see solver side iterative just under 3 minutes, and uh, 0.88 GB means 884 MB with 5 adaptive pairs it got converged, and the simulation is completed. And rest others took 4 minutes 6 minutes, and all are under just under 1.35 GB. And this is with the first order. You can see the first order basis function, second order basis function, third order basis function. As we expected, second order converged very fast compared to adaptive meshing point of view, but it took more time and more memory. Mixed order is quite good, 4 minutes and 49 seconds. And this is on filter side. Another one is a 3 by 3 array. So this is 5.9 gigahertz array. You can see 9 antenna elements and ran it on just under 6 minutes on iterative solver. And it took only 1.55 GB, and it went up to 15 adaptive passes. It's also good direct solver. So antenna array, if you are running on explicit method, 6 minutes on 9 core, it's all fine. And it's solving 9 metrics, and you can do all kind of post processing, just editing the edit source. You don't need to rerun the simulation. That's another good point here. And mixed order, which also on the basis function, it took only 6 minutes 44 seconds to simulate 2.2 GB. But I will prefer iterative solver here. Okay, and it took lesser memory in terms of computation plus the lesser simulation time. Coming here, a big helical antenna working at, I think this is working at a 3.2 gigahertz, and this is from HFSS example folder. Most of these three models which I showed you, two filter and this helical, they are from the HFSS example model. And you can see here also iterative performance pretty good. See, the direct matrix is taking 16.9 GB of memory, and the iterative, it took just under 4 minutes, 6 GB, maximum 6 GB of memory. Pretty good, and convergent under 3 minutes, 3 adaptive buses, and all others. See, the second order is took a lot of memory here. So I will prefer iterative with for lesser time, and almost how much 2.5x reduction in the memory usage. And this is solved on not on my machine. I have another machine which is about 8 core and 128 GB of RAM, and 4 minutes simulation time is pretty good. Then I ran a big simulation. Big simulation means 20 by 20 means 400 elements antenna, And this is I simulated using FADDM. You can see, as I mentioned earlier, domain decomposition performance will be good if you try to distribute across different core or different machine. And you can see direct matrix was taking 2 hour 55 and 90 GB of memory, and it took 15 adaptive bars to converge, where domain decomposition just took 15 minutes, almost 3.6x speed up in this computation. And you can see the memory reduction 90.2 GB memory, which is reduced to just under 13.4 GB, 6.6x reduction in the memory usage. And see the result. See, results are one-to-one matching between the domain decomposition and direct matrix. I'll show you how to create this antenna very easily in HFSS and how to do the beam steering also. Okay, so these are some of the example I prepared for justification to show you which solver is good for which application. So domain decomposition, I'll prefer if you're going more very big simulations. Okay, 400 ports are there and solving just under 57 minutes. I think it's pretty good performance by the HFSS solver. So let's see how this simulations are looks like. So this is a model which I talked about 9 by 9. So over here you can see in the solution setup 5.9 gigahertz, 0.02 is my S parameter convergence settings. So you can see I can choose direct solver, iterative solver, domain decomposition solver. So I'll prefer uh, direct solver, or sorry, I for this model I'll prefer iterative solver because it can give pretty good reduction in the memory usage. And these all are different solver techniques. I will go to another one. Here you can see this is the 38.5 gigahertz antenna. So instead of creating different design in this model, what I did is I created different setup. One for direct matrix, iterative, and like that I can see direct matrix, uh, then domain decomposition, iterative, and so on. So these all are the simulations which I try to summarize in that PPT. So play with this area, and it depends. It's very difficult sometimes to say which solver will be good, but take one model and see which solver can perform with lesser memory and lesser time, and choose according to that. And coming into, there is uh, one more filter which I explained it over here. Okay, so this is the filter which I showed in another one. This is also came from HFSS example. So you can find so many example projects under this open example folder. Go here, you can see transmission line, RF, microwave, filters, antennas. And if you go into, this is a helical antenna which I used for uh, simulating at a 3.5 gigahertz. And if I go back here in the filter, you can see this is a 338.5 gigahertz filter. And if I go, there are many filters, examples are here, so you can choose any of the filter and try it. And over here, RF and microwave, you can see this filter. This is a filter which I simulated for this particular designs, and you can see different you can see this is a isolator, sorry, ferrite circulator model, and ring hybrid model, T-junction, waveguide combiner. So many example files are there. And I would like to show you one example of how to create an antenna array, which are like 400 elements which I created, right? So that will be very interesting thing. What you need to do is, this is my this is my antenna element. I will copy this one and I'll just go here and create a new antenna element. Okay, and this antenna element, I will expand it, and here the radiation box are actually hidden. So this radiation box are actually hidden, so you can enable by going here and click on the open region. and see over here, this is pretty good. This is a box which is having the radiation boundary, the open radiation boundary. I'll delete this box and I'm going to create another box here. So I click on this region, and if you want to create a box, very easy. So just click on the create open region and say this is 5.9 gigahertz. I want to create a radiation box. It automatically create for you with all boundary settings. But here we are going to create a 20 by 20 array very quickly. So I'm going to delete this one and say I click over here, and I'm going to say just put a 0 centimeter in all direction, and the radiation boundary dimension is about lambda by 4 is size is sufficient. So I will prefer lambda by 4 or somewhere close to lambda by 4. So I'll say 2 centimeter is sufficient in this direction. And if I click apply, so you can see the 2 centimeter gap is generated. Because since antenna is a patch antenna, the radiation towards the backside will be very small, so I don't need 2 centimeter towards backside radiation, so I okay with 1 centimeter. This is very important. If you are creating a very big spokes, HFS need to mesh for everywhere, right? So what you need to do is you need to understand how your antenna going to perform it, and you can reduce the airbox also. So wherever the radiations are coming stronger, you make it bigger. If the radiations are smaller, you can even reduce it smaller. So what I will do is I'll just create this box, and this is a box I want it. Okay, what I will do is I'll create a box here. I'll tell you why I'm creating it. Okay, so this box I can delete it right away, and I selected this. I click on the display wireframe option so that the visibility will be good. And what I will do is I'll select this one. I'm going to create a master slave boundary around this. Now the master slave boundary name got changed. What you need to do is go here, coupled boundary, auto identify lattice pair, and select XY, click OK. So you will see that lattice pair is automatically created. What you need to do is now all the four faces are created. Top and bottom faces need to be assigned as a radiation boundary. So I'll select face selection, go here, selection mode face, and select the top face, select the bottom face, right click, and select the radiation boundary. So this is good. Now what I am going to do is this antenna is created, and here I'm going to take Control C, Control V. So one more box is selected. I'm going to hide this box by pressing Control H. Okay, and then what I'm going to do is select Control, make sure I'm doing object selection, and Control A, select everything except this box, and right click, replace with a 3D component. So you will see that the 3D component box will create. So I'll say this is my antenna, and click, you will see that everything will come under a 3D component. Okay, and now I have this box alone out of the 3D component. I will select this box, right click, replace with the 3D component. I'll say this is my blank air box. I'll show you why I'm creating this one. Click OK. Now you will see that two 3D components are created. Okay, you can see now a blank and antenna 3D components are created. Now you right click over here, and say create array, and there will be a window will open. Okay, create array, click on the visibility. So I want to create a 20 by 20 array. So if you want to create 20 by 20, put 2 extra, means 22 by 22. I'll tell you why I'm putting that. Click on the object unit cell, and select this antenna. So I want to create antenna everywhere except outer space. So I'll click something like this. So all these elements are going to create as an antenna. Okay. Okay, that was not required. Now outer face, I want to create a blank. So the blank was selected for all outer face. Coming down, and I can say select this also and click apply and close. You will see that an 20 by 20 array got created automatically in HFSS. Okay, so the blank space is nothing but the extra the finite edge of the antenna has to be considered. So you will have some air box around the antenna. So that's the reason a air box is created, and rest all the elements you can see over here. And under the setup, if I go here, double click on the solution, you can set the number of mesh adaptive passes count and enable, click on the skip 3D component array solving the adaptive passes. So enable this option, and you can select either direct or domain decomposition solver for here. So that's a comparison which I demonstrated here. You can see under this. So direct and domain decomposition. Direct was taken almost 3 hours, just under 50 minutes you are getting the simulating using domain decomposition. And if I go back to my session, uh, so as I mentioned, you can see this is the antenna array which already simulated, and you can see the domain decomposition and direct matrix solver simulation models. And if I click here, this is a area which I want to refer. So go to profile, and in the profile it will tell you how much memory it took, and how much time it took for the simulations. So adaptive, the machine took 6 seconds, and adaptive pass it took 47, and altogether about 47 minutes 57 seconds for the complete simulation. And over here you can also see the model which I talked about, the helical antenna. So this is a helical antenna, and model is already available under HFSS help file. I also want to refer one important thing to you on the frequency sweep side. On the frequency sweep, if I go and open the one of the filter model, which is band pass filter or any filter. So I'm taking this particular filter model, and I can use different types of frequency sweep in HFSS. So over here, if you see, I used interpolating sweep over here, so 0.062 to 2.4 gigahertz. And the advantage with the interpolating sweeps is you can the number of frequencies are independent of simulation time. What I mean is, if I put 1001 or 2001, the simulation time will not vary. So currently the simulation is solved for uh, solved for 501 frequency. If I put 101, it automatically updates the result with the 101. So if I double click here, you can see this S parameter is getting updated. You can see this is my 101 frequency point. Now what I'm going to do is I'm going to change my frequency points to 201, 2001 frequency points. So what I mean is, if you put 10,000 also, same time for interpolating frequencies to converge. And the time of convergence is depends on this particular quantity, 0.5 percentage of error of S parameter or maximum solutions. I'll explain you these particular two things. If you reduce this value, you will get more tighter S parameter, but 0.5 is sufficient for antenna problems. And 250 is even though if I request for 2000 points, maximum it's going to solve only 250. So if you increase it, yes, it will try to converge either on disk values or this particular value. Let's say I just updated here with 2001 points and click OK. And now you will see that S parameter will automatically update for 2001 frequency points. Okay. And if I go here and see the profile of simulation, you can see if I go a little bit up, the frequency sweeps are getting parallelized over the simulation. So if you go here a little bit up, and so the 10th adaptive pass, it got converged, and you can see up to 3 frequencies are trying to parallelize it over here. So 3 frequencies parallelizing because I'm using 6 core, 1 frequency point, 2 core for 1 frequency point. So 3 frequencies are parallelizing. You can see 3 frequencies are parallelizing, and then you can see the error level. So as you go down, you will see that the error level is coming down. So you can see over here 4%, 1%, and finally you will see somewhere close to uh, 0.00 point. If it is point less than 0.5%, its parameter will get converged. So this is how way interpolating is working. Interpolating is pretty good. For very narrow band, you can use fast sweep also. But for very wide band simulations, I will recommend always go with interpolating. That will give you the S parameter for a n number of frequency points. And also note that even if you request for 2000 frequency points, S parameter got converged within 28 frequency points. So it's all only 28 points, and it gives you the S parameter for the entire frequency band, and it will interpolate for the n number of frequency which you are asking. So these all are my suggestions for simulation. You first of all update your version. Second one is choose what should be your S parameter accuracy. 0.02 is sufficient for filter antenna problems. 0.01 or 0.005s are using for signal integrity problem where couplings are in the order of -60, -70 dB, and use mainly uh, iterative solvers. So if you are working on older versions, still go with the direct solver. Update your version and then use iterative solvers. You will see a lot of reduction in the simulation time and memory. Most of the time, simulation time can even go up higher than direct metrics sometimes, but I can guarantee you that it will take lesser memory for the simulation. So iterative solver for smaller problems, bigger domain decomposition for bigger problem, otherwise direct solver. So choose which solver is the best for your simulation. All the best for your simulation works. Bye.